Somewhere beneath you right now, so slowly that no instrument built by human hands could show you the motion in real time, a piece of the ground is shifting, not shaking, not falling, just easing, the way a body settles a little deeper into a mattress over the course of a long night. You won't feel it. Nobody has ever felt it happen. And yet it is happening, in this moment, under the valley we're about to sit in together, under every valley, under every quiet sleeping town on the planet. Let's go there now. Picture a mountain valley just before dawn. The sky above the ridgeline is the color of a bruise healing, that deep blue violet that hasn't decided yet whether it wants to be night or morning. Cold air is pooling low, the way it always does in valleys, sliding down the slopes overnight and settling around your ankles like water finding the lowest point in a room. Somewhere a creek is moving over stones, unhurried. The same sound it made an hour ago, and the same sound it will make an hour from now. There's a stillness to a mountain valley in the last dark hour before sunrise that feels almost held, like the whole basin is a held breath, waiting to be let out slowly once the light comes over the eastern peaks. You don't need to hold on to any of this. That's the first thing I want you to know, and maybe the only thing that really matters tonight. You don't need to remember the names of the mountains we'll talk about, or the numbers, or which layer of rock sits on top of which. This isn't a lesson with a test at the end. Think of it more like being read to as a child, when the story mattered less than the voice telling it, less than the weight of a blanket, and the knowledge that nothing was required of you except to lie there and let the words happen. If you drift off in the next few minutes, that's not a failure of attention. That's the whole point. Sleep whenever it comes for you. I'll still be here, in a sense, for whichever part of this you happen to catch. So let's just look, for a while, at these enormous, quiet shapes that ring the valley. Mountains have a strange effect on people. We tend to think of them as the most permanent things around us, the fixed points against which everything else moves and changes. Rivers change course, forests burn and regrow, cities rise and get abandoned and get built again on top of their own ruins. But the mountains, we assume, just stay. A person born in a village at the foot of a peak, and their great-great-grandchild born in the same village centuries later, will look up at what seems to be the same unchanging silhouette against the sky. And in a human sense, that's true. The mountain will outlast every one of us, and every language we speak, and probably every word in this sentence. But here's the strange and rather comforting thing about mountains, if you sit with it slowly enough. They aren't permanent at all. Not really. They're just very, very slow. There's a difference between something that lasts forever and something that simply moves too gradually for us to notice. And almost everything we call solid ground falls into that second category. A mountain is less like a monument, carved once and finished, and more like a wave that happens to be moving at the pace of continents instead of the pace of water. It rises. It exists for a while that might be tens of millions of years, which sounds close enough to forever from where we're sitting, and then it wears away. Every mountain you have ever seen a photograph of, every peak that's ever appeared on a postcard or a coin or the side of a mug, is in the process of becoming smaller. Some are still growing taller even now, inch by inch, so slowly that a human lifetime barely registers the change. Others peaked, so to speak, a long time ago, and have spent every year since being worn quietly down by wind and rain and the simple patient weight of time. This can be hard to hold on to, lying here in the dark, because our own sense of time is so short and so loud by comparison. We measure our lives in decades. We get impatient waiting a few minutes for water to boil, And here is this mountain outside the valley, taking 100 million years to rise, and then 100 million more to be ground back down into gravel and sand, without ever once hurrying, without ever once needing to. There's something almost restful in that, once you let it sink in. The mountain isn't trying to accomplish anything on your schedule, or any schedule at all. It exists at a pace so far outside of human urgency that urgency itself starts to feel a little unnecessary, a little optional, the way it does in the last minutes before sleep, when the day's obligations have finally stopped mattering enough to keep you awake. The planet beneath these mountains isn't a still thing either, even though it certainly feels still under your feet, and under this mountain valley, and under everywhere else you've ever stood. The ground you're imagining right now, the cold, packed earth of the valley floor, the granite of the peaks around it, sits on top of something that behaves, over long enough stretches of time, almost like a very slow, very thick liquid. Not liquid the way water is liquid, nothing you'd ever see moving, nothing you could pour into a glass. More like the pitch in an old experiment some patient scientists set up a long time ago, dripping a hardened lump of tar through a funnel just to see how long a single drop would take to fall. It took years. It took, in that particular experiment, closer to a decade for one drop to finally let go and fall into the beaker below. To anyone watching in any given moment, the pitch looked completely solid, breakable even, the kind of thing you could crack with a hammer if you were impatient enough. And yet, given enough time, it flowed anyway, drop by drop, following gravity exactly the way water does, just at a pace almost too slow for a human witness to bear. That's roughly the kind of restlessness we're talking about when we say the planet beneath the mountains is restless. Not restless like a person tossing and turning, restless the way that dripping pitch is restless, barely perceptible, almost embarrassingly slow by any human standard, and yet undeniably, patiently, endlessly in motion. Deep below the valley floor, below the mountain roots, there is a kind of very slow churning, heat rising, material shifting, pressure building in places and releasing in others, over spans of time so long that entire species have appeared and gone extinct, while a single one of these slow movements was still underway. Mountains are what happens on the surface when that deep, slow churning eventually pushes something up, or pulls something apart, or presses two enormous sections of ground against each other until the ground itself has nowhere left to go but upward. We'll get into exactly how that happens a little later, the pushing and the pressing, the way rock that seems as immovable as anything in the world can, over unimaginable stretches of time, bend and fold and lift, the way a rug bunches up if you slide something slowly underneath it. But there's no rush to get there. Right now, in this valley, before the sun has cleared the ridgeline, it's enough just to sit with the basic, strange fact of it. The mountains around you are not what they appear to be. They look eternal. They are, in truth, something closer to very old, very slow weather. Shapes the planet is still in the middle of drawing, erasing, and drawing again. The dark outside the valley is starting to soften now, just barely, the blue overhead thinning by degrees too small to name. Somewhere above the eastern ridge, the first hint of light is beginning to gather, the way it always does before it actually arrives. And before we let that light come all the way in, it's worth asking a much simpler question first, one that doesn't require any deep time or slow churning rock at all. It's worth asking what a mountain even is, in the plainest possible sense, and why the ground decided, in some places and not others, to reach so far up into the sky. To answer that, it helps to stop thinking about mountains for a moment, and think instead about the ground underneath everything. including the flattest places you have ever stood. A parking lot, a wheat field, the floor of a dry lake bed stretching flat to the horizon in every direction. All of that ground, and the ground under the mountains too, is sitting on top of the same basic structure, the same layered planet, and the differences between a mountain range and a stretch of prairie have less to do with what the ground is made of than with what has happened to it, and when, and for how long. Picture the Earth, just for a moment, not as a map or a globe sitting on a shelf, but as something closer to a soft-boiled egg, if you'll forgive the kitchen comparison this early in the morning. There is a shell on the outside, thin compared to everything beneath it, and then a much thicker, softer layer underneath that shell, and then, at the very center, something dense and hot that the outer layers are essentially floating on top of. The shell of the Earth, the part we stand on, is called the crust, and it is almost absurdly thin next to the rest of the planet. If the Earth were shrunk down to the size of that egg, the crust would be thinner than the eggshell itself, a few miles deep under the oceans, a few dozen miles deep under the continents, compared to a planet whose center lies nearly 4,000 miles down. Everything we know as solid ground, every mountain, every valley, every riverbed, is happening on the outermost skin of something enormously larger. Below that crust is the mantle, and the mantle is where the real strangeness begins, because the mantle is rock, and yet it does not behave the way rock behaves in your hand. It is solid, in the sense that if you could somehow travel down there and tap on it, it would not splash or pour. But it is also hot enough and under enough pressure that over long stretches of time it flows, the way an incredibly thick liquid flows, the way honey moves if you leave a jar of it tilted on its side and come back the next day to find it has shifted, almost imperceptibly, toward the lower edge. Geologists sometimes reach for the word plastic to describe this kind of solid, not because the mantle resembles a plastic bottle, but because it means the material can bend and deform and creep without ever actually breaking or melting into liquid. Ice does something similar, if you give it enough time and enough weight pressing down on it, which is part of why glaciers slide slowly downhill, even though the ice itself never turns to water. The mantle is doing something like that, but hotter, deeper, and unfathomably slower. That slowness is worth sitting with, because it's easy to hear the word flow and imagine something like a river, or even like that dripping pitch we mentioned before, an experiment sealed in a jar in a laboratory in Australia decades ago, where a drop of tar takes years to fall. The mantle is slower than that. Estimates vary, and honestly, this is one of those places in earth science where reasonable scientists still argue about exact numbers, but a rough sense of the scale is that material within the mantle might move a few inches a year, something like the pace at which your fingernails grow. Almost nothing from where you're lying right now, and yet run that pace out over 10 million years, over 100 million years, over the kind of time span that swallows the entire history of the dinosaurs and asks for more, and a few inches a year adds up to thousands of miles of material shifting, rising, sinking, and shifting again. That shifting has a name, or at least the pattern it falls into has a name, and it's called convection. And if you have ever watched a pot of water just before it boils, you have already seen a rough, fast, kitchen-sized version of it. Heat near the bottom of the pot makes that water expand slightly and rise. Cooler water near the top sinks down to take its place, and the whole pot organizes itself into slow rolling loops, rising in some spots, sinking in others, long before any of it actually starts to bubble. The mantle does something like this too, heated from below by the Earth's core, which is hotter than the surface of the sun in some estimates, cooling near the top where it meets the crust, and organizing itself, however slowly, into enormous looping currents of rising and sinking rock. It is not a fast, visible churn like the pot of water. It is closer to something you would need a time-lapse camera running for 100 million years to actually see moving. But the pattern, rising here, sinking there, material slowly cycling through the depths and back again, is recognizably the same kind of motion, just stretched out to a timescale that human beings were never built to perceive directly. Now, here is where the crust comes back into the story, because the crust is not one continuous shell wrapped smoothly around the planet the way an eggshell wraps around an egg. It is broken, cracked really, into a number of large pieces, called plates, fitting together like the panels of a soccer ball, or perhaps more usefully, like a cracked windshield, where the glass is still mostly intact and still mostly in one piece, but is nonetheless divided by long fracture lines into distinct sections that can, ever so slightly, move independently of one another. There are roughly a dozen or so major plates, depending on how finely you want to divide some of the smaller, disputed edges, and they carry the continents and ocean floors around on their backs, the way a raft carries whatever happens to be sitting on top of it. And because these plates are resting on that slow churning mantle underneath, riding on top of those long, rolling currents of rising and sinking rock, the plates themselves are being carried along too, dragged and pushed and pulled by forces working on them from below and from the sides, moving at roughly the speed, again, of a fingernail growing. Where those plates meet each other is where nearly everything interesting happens to the surface of the earth. And there are really only a few basic kinds of meetings, even though the results can look wildly different depending on the details. Sometimes two plates are pulling apart from each other, drifting in opposite directions, and where that happens, the ground stretches and thins, sometimes cracking open into long valleys, sometimes letting hot material well up from below to fill the gap, a process called rifting, and it is slowly happening right now, quite famously, along a great crack running down through eastern Africa. Sometimes, instead, two plates are grinding sideways past each other, neither one pulling away nor pushing forward, but scraping alongside its neighbor the way two cars might sideswipe each other in slow motion, and where the rock catches and holds instead of sliding smoothly, pressure builds up along the boundary until it finally releases all at once, which is one of the basic ingredients of an earthquake. And sometimes, most relevant to the ground you happen to be lying on this morning, two plates are pushing directly into one another, compressing the crust between them the way two hands might slowly press together with a folded towel caught between the palms. That compression is where mountains genuinely begin, though the story is far from finished at this point. Rock under enough sideways pressure does not simply crumble the way you might expect glass or concrete to crumble. Given enough time and enough heat and enough confining pressure from all directions, rock bends. It folds the way that towel folds between your palms, the way a rug bunches into ridges if something slides slowly underneath it, and it also breaks, in places, along long cracks called faults, where one section of crust is forced up and over the section beside it, or shoved downward beneath it, in movements that can be sudden and violent on a human timescale, even while the overall collision unfolds across millions of years. Fold enough rock, break and stack enough of it along enough faults, over a long enough collision between two enormous pieces of moving ground, and eventually there is nowhere left for that compressed, crumpled, thickened crust to go except up, higher and higher, until what was once a stretch of ordinary, unremarkable ground becomes something with real elevation, something that throws a shadow across a valley in the last dark hour before sunrise. Picture that towel again, folded gently between two palms. If you push slowly and evenly, The fabric rises into long, rounded ridges, each one running roughly parallel to the direction of the push, with valleys dipping between them. This is close to what geologists mean when they talk about fold mountains, and the reason it matters is that rock, under the right conditions of heat and pressure, behaves surprisingly like fabric rather than like something brittle. Deep in a mountain-building collision, layers of sedimentary rock that once lay perfectly flat on an ancient seafloor can be bent into long, graceful arcs, sometimes gently undulating, sometimes folded so tightly and repeatedly that a single layer of rock, if you could trace it with a finger, would zigzag back and forth dozens of times within the space of a single cliff face. The Appalachian Mountains of eastern North America show this kind of folding beautifully, though softened now by an almost unimaginable amount of time. And the Himalayas, still actively rising as the Indian plate continues to press northward into Asia at a pace of perhaps 2 inches a year, roughly the speed a fingernail grows, show folding in its rawer, younger form, with rock layers bent so dramatically that in certain valleys you can see, plain as daylight, marine fossils, the remains of ancient sea creatures, sitting in stone many thousands of feet above sea level. That detail unsettled more than one 19th-century naturalist. When early surveyors and geologists found fossilized shells high in the Himalayas, it took real intellectual courage, and no small amount of patience with skeptical colleagues, to accept what the evidence was quietly saying, that this rock had once rested at the bottom of an ocean and had since been folded and lifted to among the highest points on the planet. Fold mountains, though, are only one way that compressed crust finds its way upward. Sometimes the rock does not bend so much as it breaks, cleanly, along a more or less straight line, and one enormous block of crust is shoved upward relative to its neighbor, tilting as it rises like a trapdoor lifted from underneath. Geologists call these fault block mountains, and if you have ever seen the Sierra Nevada range in California, you have seen this process on full display, whether you realized it at the time or not. The eastern face of the Sierra Nevada rises with startling steepness, almost like a wall, while the western slope descends far more gradually, tilting away in a long, gentle ramp. That asymmetry is the signature of a single block of crust tipping upward along a fault, the way one edge of a trapdoor lifts while the hinge stays low. The Teton Range in Wyoming tells a similar story, and it tells it with unusual clarity, because the block that rose to form the mountains sits right beside the block that dropped to form the valley floor at their base, with almost none of the gentler, gradual foothills you might expect leading up to it. Stand at the valley floor there and look up, and the mountains simply begin, abruptly, a wall of rock rising more than a mile above the sagebrush plain, with no soft transition at all. That abruptness is not an illusion of perspective. It is the visible edge of a fault, a place where the ground itself decided, at some point in the deep past, to break rather than bend, and has kept moving in small increments ever since, an inch or two at a time, with long, silent centuries in between. There is a third path upward, and it has nothing to do with folding or breaking rock through sideways pressure at all. Sometimes a mountain is built not by squeezing the crust, but by feeding it, adding material to it from below, the way a drip of wax slowly builds a small cone on a candlestick if you let it fall in the same place again and again. This is how volcanic mountains grow. Molten rock, less dense than the solid crust around it, rises from deep within the earth and, when it finds a path to the surface, erupts as lava, ash, or both, and each eruption adds another thin layer to the pile. Do this enough times, over enough centuries, and you get a mountain built entirely from the inside out, layer stacked upon layer, rather than lifted or crumpled from the sides. Mount Fuji in Japan grew this way, its famously symmetrical cone, the product of countless eruptions, each one draping fresh material evenly down every slope, the way wax drips evenly if the candle never moves. Some volcanic mountains form directly above the collision zones we have already discussed, where one plate is forced down beneath another and slowly melts under the tremendous heat and pressure of that descent, feeding magma back up to the surface hundreds of miles from the boundary itself, which is part of why a whole chain of volcanoes, the Cascades, runs up through the Pacific Northwest of the United States, each peak a separate vent above the same deep, slow-melting process below. Other volcanic mountains form far from any plate boundary at all, over what some geologists describe loosely and with real ongoing scientific discussion about the details as a persistent hotspot in the mantle, a place where heat rises steadily regardless of which piece of crust happens to be drifting overhead at the time. The Hawaiian Islands are the clearest illustration of this, a whole chain of volcanic peaks strung out across the Pacific, each one older than the last as you move away from the youngest, still active island, because the crust above the hotspot has been slowly sliding along for millions of years, like a sheet of paper dragged slowly over a candle flame held steady underneath, leaving a trail of scorch marks rather than just one. Not every rise in the land needs folding, faulting, or fire at all, though. Sometimes a broad, gentle upward bulge appears in the crust simply because something is pushing up from below without breaking through to the surface, the way a fist pressed slowly against the underside of a blanket will lift the fabric into a smooth dome without ever tearing it. The Black Hills of South Dakota formed something like this, a wide, rounded uplift where older rock was pushed upward, and the softer rock that once lay above it has since worn away, exposing the ancient, harder core beneath, in a broad dome rather than a sharp peak. And closely related to this idea, though grander in scale, is the plateau, a place where an enormous area of crust rises together, evenly, as a single unbroken slab rather than folding into ridges or breaking into blocks. The Colorado Plateau, that vast elevated tableland stretching across parts of Arizona, Utah, Colorado, and New Mexico, rose in this steady, even way, and it is precisely because the rock layers there stayed relatively flat and undisturbed, while the whole plateau lifted, that rivers like the Colorado were later able to carve straight down through mile after mile of neatly stacked rock, exposing a clean, orderly slice through hundreds of millions of years of Earth's history in the walls of the Grand Canyon. And then there are the oldest mountains of all, the ones that have been worn down so thoroughly and for so long that what remains today is not really the mountain at all, but its ancient root, the deep, hardened core that once lay miles beneath a much taller peak. The Appalachians belong here too, in this sense, alongside their folding, because those mountains are thought to have once stood as tall as the Himalayas stand today, before hundreds of millions of years of rain, ice, and rivers wore them down to their present, gentler height, patiently, the way water dripping onto a single spot will eventually hollow even the hardest stone. What you are left with in a landscape like that is something almost like a fossil of a mountain range, worn low and rounded, its violent birth softened into something a traveler might now cross on a quiet, easy afternoon hike, hardly guessing at the scale of what once stood there. It raises a gentler question, though, one worth sitting with as the night goes on. If mountains can be worn down this completely, this patiently, what exactly does the wearing down, and how slowly does it actually happen? Let it sit for a moment, though, this question of wearing down, because to answer it properly, we have to go somewhere unexpected, somewhere far beneath the mountain itself, down into the rock's own quiet, slow-motion history, long before it ever became a peak at all. Rock, it turns out, is not the fixed, unchanging thing it appears to be when you run your hand along a cliff face, cool and solid under your palm. It has a life, of sorts, one that unfolds over such long stretches of time that from where we stand, rock simply looks like the definition of permanence, the word we reach for whenever we want to describe something that will not change. But squeeze it hard enough, heat it slowly enough, and bury it deep enough, and rock will change into something else entirely, keeping the same atoms, largely, but rearranging them, the way a lump of clay left in a potter's hands becomes a bowl without ever stopping being clay, without a single new particle being added or taken away. Consider a single grain of sand resting on the floor of an ancient seabed, perhaps 400 million years ago, in a shallow, warm ocean that no longer exists in any form you could point to on a map today, an ocean with no name, because no one was alive yet to name it. That grain settles, along with countless billions like it, into a soft layer of sediment, and over time, as more sediment piles on top, year after year, century after century, the weight above begins to press down, squeezing the water out from between the grains, cementing them together into solid rock. This is sandstone, one of the more familiar transformations, something you may have already touched without thinking about it, in a garden wall or a canyon face, and it seems, at this point, like a finished story. But it is not finished. If that layer of sandstone happens to lie in the path of two continents drifting slowly toward each other, as we described happening to form great mountain chains, then its story is only beginning. As the collision proceeds, and one great slab of crust begins to override another, or as thick folds of rock pile up and push down into the earth beneath their own weight, that sandstone can be carried downward, deeper than any drill has ever reached, deeper than the deepest mine shaft ever sunk by human hands, down to where the temperature climbs to several hundred degrees, and the pressure becomes so immense that it would be measured in thousands of times the pressure of the air pressing on you right now, sitting quietly wherever you are. Down there, the rock does not melt, not yet, but it does not stay the same either. The minerals within it, the tiny crystals of quartz and clay and feldspar, begin to soften just enough under all that heat and pressure to recrystallize, to rearrange their internal structure into new minerals that are more stable at these extreme conditions. The way ice under enough pressure will behave differently than ice sitting quietly in a freezer, flowing almost like a thick liquid at the base of a glacier, even while it remains, technically, solid. This process is called metamorphism, a word that simply means change of form, and it is one of the quieter, stranger truths about the deep architecture of mountains. Much of the rock inside a great mountain range was not always mountain rock at all. It was seafloor once, or a river delta, or a stretch of open ocean thick with tiny drifting shells, before pressure and heat folded it into something new, something that no longer resembles at first glance where it came from. Under this kind of transformation, sandstone can become quartzite, a rock so hard and glassy that it rings almost like stone struck against stone, quite unlike the soft, crumbly sandstone it once was, the kind of stone that will spark rather than crumble if you strike it with steel. Shale, the fine, flaky rock formed from ancient mud settling in still water, becomes slate, the material once split into thin, even sheets for roofing tiles and writing boards, then phyllite, with its faint, silky sheen, then schist, coarser, and more visibly crystalline, each name marking a further step deeper into heat and pressure. Each stage visible under a microscope as slightly larger, slightly more organized crystals, all lined up in the same direction, like a stack of pages, pressed until every page falls into perfect alignment, or, like iron filings, arranging themselves along the invisible lines of a magnet. And limestone, the rock built from the accumulated shells of countless ancient sea creatures, tiny and pale, compressed over millions of years on the ocean floor into something dense enough to build with, becomes marble, the very stone that Michelangelo selected by hand from quarries in Carrara, in the mountains of Tuscany, running his fingers along the surface of a block to judge its quality before it was ever cut, tapping it sometimes to listen for hidden flaws, never quite knowing, of course, that the smooth white stone beneath his hands had begun its existence as the soft remains of sea life, settling gently onto an ocean floor that vanished long before humans existed to give oceans names at all. It is worth pausing on marble, for a moment, because it captures something quietly remarkable about mountain building. The stone in a cathedral ceiling, or in the veins of an old countertop, cool under a hand late at night in a quiet kitchen, may have been ocean sediment before it was rock at all, and mountain before it was marble, and quarry before it was art. Every layer of that history is folded into the material itself, compressed and carried forward, even if nothing about its polished, finished surface gives any hint of the transformation it passed through to get there. No visible seam, marking where seafloor ended and sculpture began. But metamorphism is not the end of the story either, because if you keep pushing rock deeper, keep raising the temperature and pressure further still, eventually you cross a threshold where the rock stops merely rearranging itself and begins, instead, to melt. Not all at once, and not entirely, in most cases, but partially, the way a chocolate bar left in a warm car will start to soften and slump at its edges, losing its sharp corners, long before it ever becomes a full liquid pool spreading across the seat. This partial melting produces magma, molten or semi-molten rock, which, being less dense than the solid rock around it, tends to rise, slowly, sometimes over millions of years, working its way upward through cracks and weaknesses in the crust above, the way a warm bubble of oil rises unhurried through a thick pot of soup left simmering on a low flame, taking its time, never in a hurry to reach the surface. Sometimes that magma reaches the surface and erupts, cooling quickly into the fine-grained volcanic rock that builds cones like Fuji or Rainier, their smooth, symmetrical slopes a direct record of how many times lava and ash have layered themselves, one eruption at a time, over thousands of years. But often, and this is the part that matters most for understanding what lies inside a mountain range, the magma never makes it that far. It stalls somewhere within the crust, cooling slowly over thousands or even millions of years, crystallizing gradually into large, visible crystals, because slow cooling gives crystals time to grow, patiently, undisturbed, the same way a sugar solution left undisturbed for a long stretch on a windowsill will form larger, more defined crystals than one that is cooled quickly under a tap. This slow, deep cooling produces granite, the coarse, speckled rock you can see studded with visible flecks of quartz, feldspar, and mica if you look closely at the polished stone of an old building's front steps, worn smooth by generations of footsteps, or at the exposed granite domes of a place like Yosemite in California, where valley glaciers later scraped away the softer rock above to reveal the hardened granite heart that had solidified deep underground long before any ice ever touched it, long before there was a valley there to hold the ice at all. So beneath the visible peak of almost any major mountain range, buried at depths that no one will ever walk to directly, there sits a kind of layered, tangled record, sedimentary rock transformed into metamorphic rock melted and resolidified into granite, all of it folded, faulted, and shuffled together by the same slow collision that pushed the mountains skyward in the first place. Geologists who study these deep rocks, cutting thin, near-transparent slices to examine under polarized light, watching colors bloom across the crystals that no eye could see in ordinary daylight, are essentially reading a kind of diary, one written not in words but in mineral grains. Each crystal shape and alignment recording something about the temperature and pressure the rock experienced at some particular moment, buried somewhere within an ocean or a continent or a mountain route that vanished long before anyone was there to see it vanish. And that idea, that the rock beneath your feet on a quiet mountain trail might carry within it the compressed, transformed memory of a seafloor that existed hundreds of millions of years earlier, leads naturally to a further question worth turning over slowly, in no rush at all. How do we actually know how old any of this is? And how can anyone possibly read a number, in years, out of a piece of stone? That question about the calendar hidden inside stone is one worth sitting with, but it can wait for its own quiet turn later, because there is a simpler, more immediate question pressing in first, one that anyone standing at the base of a mountain range might ask without needing any geology at all. Does a mountain just sit there, finished, once it has been pushed up out of the ground? And the answer, as it usually is with anything that seems permanent, is no. A mountain is never really finished. It is being built and unbuilt at the same time, rising from below through the same slow collision of plates that folded those deep rocks in the first place, while up above, almost everything else in the world is quietly working to wear it back down. Wind, rain, frost, rivers, gravity, and a whole slow chemistry of dissolving minerals are all, in their own patient ways, taking the mountain apart, even as the earth keeps pushing more of it upward. It is a bit like a sandcastle, built right at the tide line, except stretched out over millions of years instead of a single afternoon, with someone still piling sand on top, even as the water keeps licking it away from the base. Frost is one of the quieter demolition crews, and one of the most effective, especially high up, where the temperature swings back and forth across the freezing point almost every single day. Rain or meltwater seeps into the smallest cracks in a rock face, cracks too fine to notice at first, hairline seams left over from the stresses of the rock's original formation or from earlier freezing. When night falls and the temperature drops, that water freezes, and here is the detail that makes the whole process work. Water is unusual in that it expands as it freezes, rather than contracting, growing by roughly 9% in volume as it turns to ice. Anyone who has left a glass bottle of water in the freezer too long and come back to find it split open, its contents frozen mid-crack, has already felt this force firsthand, on a small and inconvenient scale. Now imagine that same expanding wedge of ice working inside a crack in solid granite, prying it open by some almost invisible fraction of a millimeter, then melting the next afternoon, then freezing again the following night, over and over, season after season, year after year. Nothing about any single freeze does very much, but repeated across centuries, this freeze-thaw cycle is enough to split boulders clean in half and to shatter cliff faces into loose, angular rubble, which then tumbles down and piles up at the base of a slope in the long, sloping aprons of broken stone that hikers know as talus or scree, that unstable, ankle-turning gravel field lying beneath almost every steep mountain wall in cold country. Rain does its own separate kind of work, both mechanical and chemical at once. Falling on bare slopes, it gathers into rivulets, and rivulets gather into streams, and streams cut downward into whatever rock lies in their path, grain by grain, carrying that worn material away as sediment, the fine silt that turns a mountain river the color of tea or clay after a hard storm. Leonardo da Vinci, sketching in his notebooks around the turn of the 16th century, noticed something like this himself, observing how rivers seemed to be slowly lowering the very hills he watched them flow through, an idea that ran well ahead of the geology of his own time. Given enough time, a river does not just flow across a landscape, it carves one, cutting the narrow, steep-walled valleys typical of young, actively rising mountains, valleys shaped roughly like the letter V when you look at them in cross-section, because the water is working fastest right at the bottom of the channel, slicing downward far more than it spreads outward. The Colorado River, patiently sawing through the layered rock of what is now the Grand Canyon over the course of several million years, is really only doing at an enormous, almost unbelievable scale what every small mountain stream is doing in miniature, wearing a groove into stone, the way a cook wears a groove into a wooden cutting board, one thin slice of contact at a time, repeated so many thousands of times that the groove finally becomes impossible to ignore. Wind, by comparison, works more slowly in most places, since air alone is far less effective than water at physically dislodging rock. But wind still carries sand and dust picked up elsewhere, and in dry, exposed, high-altitude terrain, where there is little vegetation to hold soil in place and little rainfall to soften the process, that wind-borne sand acts almost like a slow, natural sandblaster, scouring the surface of exposed rock, polishing some faces smooth while grinding others into strange, faceted shapes called ventifacts, stones sculpted with flat, wind-carved sides that look almost too deliberate to be natural. It is a gentler contributor than frost or running water in most mountain settings, but in the driest, most wind-scoured high country, over a long enough stretch of time, even air carrying grit becomes a sculpting tool. Then there is gravity, which never really does anything of its own accord so much as it simply waits, patiently, for everything else to loosen its grip. Once frost has cracked a boulder free, once rain has undercut a slope, gravity is what finally pulls the loosened material downward, sometimes in a slow, barely perceptible creep of soil no faster than the growth of a fingernail, and sometimes in a sudden, thunderous rock slide or avalanche that can rearrange an entire mountainside within a matter of seconds. Almost everything that other forces loosen eventually gives in to gravity in one way or another, tumbling, sliding, or slumping downhill until it settles somewhere lower, in a stream bed or a valley floor, where it may sit for a very long time, or may be picked up all over again by the next flood and carried farther still. Underneath all of this mechanical breaking, cracking, and tumbling, there is also a quieter, less visible kind of erosion happening at the level of the minerals themselves, called chemical weathering, and it works less like a hammer and more like a very slow, very patient kind of dissolving. Rainwater is never perfectly pure. As it falls through the air, it absorbs a small amount of carbon dioxide, forming a weak carbonic acid, the same mild acid, incidentally, that gives carbonated water its faint tang. That slightly acidic rain, over long stretches of time, can dissolve certain kinds of rock outright, which is why limestone mountains often develop the pitted, fluted, cave-riddled landscape known as karst, full of sinkholes and underground caverns, carved not by any river's mechanical force, but by centuries of rock simply going into solution and being carried away, molecule by molecule, in the water. Other minerals do not dissolve so cleanly, but instead transform where they sit. Iron-bearing minerals react slowly with oxygen in the air and water, rusting in place much the way an old iron gate left out in the rain turns from gray to a deep reddish-orange, which is part of why so many mountain rocks carry those warm, rust-colored streaks and stains across their gray faces. Feldspar, one of the common minerals that makes up granite, slowly breaks down through contact with water into clay, the same soft, fine-grained material that potters shape on a wheel, which means that granite, that hard, speckled rock born from magma cooling miles underground, is itself slowly turning back into something closer to soil, given enough centuries of rain. All of these forces, frost and rain and rivers, wind and gravity and slow chemical dissolving, work on a mountain range at the very same time that deep tectonic forces are still pushing it upward, and this is really the detail worth holding on to as everything else grows quieter. A mountain range can be actively rising and actively eroding simultaneously, the two processes running side by side rather than one waiting politely for the other to finish. In some ranges, like parts of the southern Alps of New Zealand, the uplift and the erosion are moving at such closely matched paces that geologists describe the range as being in something close to a steady state, rising and wearing down at nearly the same rate, so that the mountain, in a strange sense, is standing still even while every part of it is in motion. It is one thing to imagine a mountain as something the earth built once and then left alone. It is a different, quieter thing to imagine it as something the earth is still building and still dismantling in the very same breath. And among all of erosion's tools, there is one that works more slowly, more heavily, and more decisively than any of the others, one made of nothing more than compressed, patient ice. Snow, when it first falls high on a mountain, is almost nothing. A single flake weighs less than a whisper, six-sided and delicate, the kind of thing that seems like it would disappear the moment it touched anything solid. But mountains are patient and cold, and what falls in one season does not always leave before the next season's snow arrives on top of it. Layer settles on layer, and the weight of all that new snow presses down on the old, squeezing out the air pockets between the crystals the way a hand might slowly flatten a pile of loose cotton into something dense and compact. The delicate, six-sided shapes are crushed and rounded and pressed together until the snow is no longer really snow at all, but something in between, a grainy, granular substance called fern, which looks a little like the crusty, refrozen snow you might find at the bottom of an old snowbank in early spring, the kind that crunches under a boot instead of sinking softly. And if the cold holds, if summer never quite manages to melt away what winter left behind, the fern keeps compressing, year after year, the air squeezed out further and further, until what remains is no longer granular at all, but a solid, blue-tinted mass of ice, dense enough that it no longer lets light pass through the way ordinary ice does, but instead absorbs the red end of the light and lets only the blue scatter back, which is why the deep ice at the heart of a glacier often looks less like frozen water and more like a piece of the sky. This place, high on the mountain, where more snow falls each year than melts away, is called the accumulation zone, and it is really the birthplace of every glacier, the quiet nursery where ice is slowly, wordlessly assembled out of nothing more dramatic than snow that simply never got the chance to leave. But ice, unlike snow, does not just sit still once it has formed. Ice, under enough pressure and enough of its own weight, behaves less like a rigid solid and more like a very slow, very thick liquid, something closer to cold honey than to a window pane. This is not because it is somehow secretly wet or soft, but because the crystals inside the ice are able to slide against one another, layer over layer, when squeezed hard enough by the tremendous weight of everything piled on top. A block of ice 100 feet thick, sitting in a mountain basin, presses down on itself with enough force that it begins, almost imperceptibly, to move, flowing downhill under its own weight, the way pancake batter spreads slowly across a hot pan, not because anyone is pushing it, but because gravity is pulling on something too dense and too heavy to simply stay where it started. This flowing river of ice, moving perhaps a few inches a day in some places, a few feet a day in others, is what people mean when they say glacier, and it behaves, in almost every meaningful way, like a very slow, very cold river, filling valleys, following the lowest and easiest path down the mountain, carrying things along with it and leaving things behind. And because it behaves like a river, it does something a river of water could never quite do in the same way. It carves. Water is soft enough that it slips around obstacles, finding cracks and gaps, wearing things down through countless small collisions of drop against stone. Ice, especially ice loaded with rock fragments frozen into its underside like grit pressed into sandpaper, does not slip around obstacles so gently. It grinds against them, scrapes against them, drags boulders and pebbles and sharp broken stone along the valley floor and up against the valley walls with a slow, relentless pressure that water alone could never manage. Where a glacier begins, high on the mountain in that same basin where the snow first accumulated, this grinding action carves out a distinctive, bowl-shaped hollow in the rock, something like the shape a spoon leaves in a container of ice cream after it has been dragged and twisted through it many times, steep-walled on 3 sides and open on the 4th, where the ice eventually flows out and downhill. Geologists call this hollow a cirque, from a French word meaning something close to circle or arena, and if you have ever stood at the base of a mountain and seen a broad, amphitheater-shaped basin high on its flank, walled in by cliffs on 3 sides, you were very likely looking at the empty seat left behind by a glacier that has long since melted away, the shape of the ice preserved in the shape of the stone even after every trace of the ice itself is gone. When 2 cirques form on opposite sides of the same ridge, each one slowly eating backward into the mountain as its glacier grinds away at the rock, the ridge between them can be worn thinner and thinner, sharpened from both sides at once, until what remains is a narrow, blade-like edge of rock, steep enough to walk along the way you might balance on the top of a fence, if the fence were made of stone and the drop on either side were several hundred feet. This is called an arête, and it is one of the more striking things a glacier leaves behind, a knife-edge ridge carved not by anything cutting downward, but by 2 hollows eating inward from opposite directions until they meet in the middle with almost nothing left between them. And when 3 or more cirques form around a single peak, each one gnawing inward from a different side, the mountain at the center can be whittled down into something dramatically pointed, a steep, pyramidal summit rising above the surrounding ridges on every side. This is called a horn, and the most famous example in the world is probably the Matterhorn, on the border between Switzerland and Italy, whose severe, 4-sided pyramid shape, so recognizable that it has been used as the model for chocolate bar wrappers and amusement park mountains, is not really the mountain as it was originally built by tectonic uplift at all, but the mountain as it has been sculpted afterward, sharpened on 4 sides by 4 separate glaciers working slowly inward over hundreds of thousands of years until almost nothing remained of the original, blunter shape. Lower down, where the ice flows out of these high basins and moves through the existing valleys of the mountain range, it carves the valley itself into a distinctive shape. A river, cutting downward with running water, tends to carve a valley shaped like the letter V, narrow and pointed at the bottom, because water concentrates its erosive power along the lowest line, the very center of the stream bed. A glacier does not behave this way. Its ice fills the entire width of the valley floor, pressing outward against the walls as much as it presses downward against the base, grinding the sides of the valley just as steadily as it grinds the bottom. The result, once the ice eventually melts away and the valley is finally visible again, is a broad, rounded floor and steep, almost vertical walls rising up on either side. a shape much closer to the letter U than to the letter V. These U-shaped valleys are one of the clearest signatures a glacier leaves on a landscape, and once you know to look for them, they become almost unmistakable. A wide, flat-bottomed trough running between the mountains where a narrower, more angular river valley would otherwise have formed. As the glacier moves, it also carries an enormous, constant burden of broken rock along with it, fragments plucked from the cirque walls above, pieces ground loose from the valley floor and sides below, boulders the size of houses, riding along inside or beneath the ice, like cargo on a very slow barge. Where the leading edge of the glacier finally stops advancing, where the melting at its lower end matches the flow arriving from above, all of this carried rock is simply dropped in place, piling up in ridges of loose, jumbled debris called moraines, unsorted mixtures of boulders, gravel, sand, and fine rock flour, all heaped together in a way that water, which sorts its sediment carefully by size and weight as it flows, would never produce. And when a glacier finally retreats, when a warming climate or a changing snowfall pattern means that more ice melts each year than accumulates, it often leaves one particular kind of gift behind in the hollow where it once sat, or the valley through which it once flowed. That gift is often a lake, a body of water pooling in the very bowl the glacier carved out of the mountainside, held there by the ring of rock and moraine debris the ice left behind like a dam it built without ever intending to. These little lakes, often startlingly blue or a pale, milky green from the fine rock flour still suspended in them, sit tucked into high mountain basins all over the world, and sometimes a whole series of them will form in a single valley, one below another, connected by short streams tumbling from lake to lake in what geologists sometimes call a string of pearls, though the more common term is simply paternoster lakes, named for their resemblance to the beads of a rosary. And it is here, in these quiet, cupped hollows of stone, that we can finally follow the mountain's water forward instead of backward, because a lake fed by a melting glacier is only ever a pause, a brief holding pattern in a journey that began long before the ice formed and will continue long after it is gone. Most of a mountain's water, though, never passes through a glacier at all. It begins its life as ordinary snow, falling in winter across the high slopes and settling into the deep, compacted layers that accumulate over months or years, a season's worth of storms, packed down into something you could call, without stretching the word too far, a kind of frozen reservoir. Snow is an unusually good way to store water, better in some ways than a lake or a tank, because it releases what it holds, slowly, gradually, in step with the warming of the seasons rather than all at once. A heavy rainstorm runs off a landscape in hours. A mountain snowpack releases its water over weeks and months, through the long stretch of spring and into early summer, feeding streams steadily, rather than in a single overwhelming pulse. This is one of the quieter reasons mountains matter so much to the places around them. They are not just sources of water, they are timers, spreading out the delivery of that water across the part of the year when it is most needed and least likely to simply fall as rain. As the snow melts, some of the water runs immediately across the surface, gathering into the thin threads of meltwater you might see trickling down a slope in early summer, threads that join other threads until they become a proper stream, tumbling over rocks, cutting its own small channel deeper with each season that passes. But a good portion of the meltwater does something less visible. It sinks. It seeps down through soil, through cracks in the bedrock, through the loose, permeable rubble left behind by the glaciers and the frost shattering that came before them, and it keeps going until it reaches a layer of rock or sediment saturated enough to hold it, a zone hydrologists call an aquifer. You can think of an aquifer less like an underground lake, which is the image most people carry around in their heads, and more like a very dense, very slow sponge, a body of rock whose pores and fractures are filled with water that moves through it at a pace measured not in hours but sometimes in decades. Some mountain aquifers are shallow and quick to respond to a wet winter. Others are old, self-contained systems that have been slowly filling and slowly draining for centuries. Water that fell as snow before certain cities even existed, now finally emerging from a spring somewhere in the valley below. And springs themselves are worth pausing on, because there is something almost quietly miraculous about them if you think about the mechanics for a moment. A spring is simply a place where the water table, the upper surface of all that saturated rock, happens to intersect with the surface of the ground, so that water, which has been traveling underground, sometimes for a very long way, suddenly has nowhere left to go but out. Mountain springs often emerge cold and remarkably clear, having been filtered, slowly and thoroughly, through hundreds of feet of rock and gravel on their way down, each layer straining out sediment and impurities, the way a series of increasingly fine sieves might. This is part of why so many towns throughout history situated themselves near mountain springs rather than near rivers lower down, where the water had already picked up sediment and sometimes contamination from everything upstream. A spring offered water that was, in a sense, still new, still close to its origin as snow or rain, not yet mixed into the busier, muddier traffic of a full river system. From springs and surface streams alike, the water continues downhill, small channels joining larger ones in a pattern that looks, from above, almost like the branches of a tree traced backward, a shape hydrologists call a drainage network. Mountains are, in this sense, the beginning of nearly every river system on the continents, the high, cold birthplace from which water sets out on a journey that might end only a few dozen miles away, or might, in the case of the largest river systems, continue for thousands of miles before finally reaching an ocean. And people, understandably, tend to settle along the routes these rivers take, sometimes very close to the mountains themselves and sometimes remarkably far away. Some of the water flowing through the taps of cities on the dry plains far from any peak began, not so long before, as snow falling silently onto a ridge the people living there may never have seen and might not even know the name of. The presence of a mountain range does something else to water as well, something that has less to do with rivers running downhill and more to do with the atmosphere itself, with the great, slow currents of moist air constantly moving across the surface of the earth. When a mass of air carrying moisture, picked up perhaps from an ocean many miles away, encounters a mountain range, it has no choice but to rise, because the rock is simply there, solid and unmoving, and the air must go up and over it if it is going to continue on its path at all. As air rises, it cools, and cool air is able to hold less moisture than warm air, so the water vapor it was carrying begins to condense, forming clouds, and often falling as rain or snow on the side of the mountain, facing the moisture's approach. By the time that same air has crested the highest ridge and begun descending the far side, it has already given up much of what it was carrying. Descending air also warms as it sinks, which only makes it more capable of holding on to whatever moisture remains rather than releasing it. The result is a landscape that can look almost like two entirely different climates sitting side by side, separated only by the width of a mountain range. One slope is green, often thick with forest, regularly soaked by rain or blanketed in deep snow. The other slope, sometimes only a short distance away as measured in a straight line, is dry, sometimes startlingly so, supporting only sparse grasses or true desert vegetation, because the moisture that might have fallen there was already spent on the windward side before the air ever arrived. This pattern has a name, the rain shadow, and it explains some of the more puzzling contrasts travelers notice when crossing a major range. Why a valley on one side smells of damp pine and a valley on the other, not so very far off, smells instead of dust and dry sage. What a rain shadow reveals, more broadly, is that mountains do not just channel the water that falls on them, they actively reshape where water falls in the first place, bending the paths of moving air the way a boulder bends the current of a stream, forcing moisture to release itself in one place and denying it to another. To understand a mountain range fully, then, it helps to think of it not only as rock, and not only as the birthplace of rivers and springs, but as a kind of enormous, permanent obstacle sitting directly in the path of the wind. Consider, for a moment, what it actually feels like to climb one of these obstacles from its base to its summit, not in the abstract, but step by step, the way a person walking a trail actually experiences it. At the bottom, the air is thick with oxygen, dense and easy to breathe, so ordinary that most people never think about it at all. But that air has weight, and all of it is being pulled downward by gravity, which means the deepest layers, the ones closest to sea level, are compressed by everything stacked above them, the way the bottom book in a tall stack bears the weight of every book piled on top. Climb higher, and there is simply less air above you pressing down, so the air around you spreads out, becomes thinner, holds fewer molecules of oxygen in every breath a person draws. This is not a gradual curiosity that only scientists notice. It is something the body registers directly, and sometimes painfully. A person who lives at sea level and travels quickly to a city like La Paz, in Bolivia, sitting well over 11,000 feet up in the Andes, may find themselves short of breath simply climbing a flight of stairs, their heart racing to compensate for air that holds perhaps 2/3 the oxygen it would at home. Early European travelers to high mountain regions sometimes described this feeling in almost supernatural terms: a heaviness, a kind of drunkenness, headaches that would not lift, because they had no framework yet for understanding that the very substance keeping them alive had simply become scarcer around them. Given enough time, the body can adjust, producing more red blood cells to carry oxygen more efficiently, and populations that have lived at extreme altitude for many generations, in the Andes, in Tibet, in parts of Ethiopia, show inherited biological adaptations that let them thrive where a newcomer would struggle, evidence written directly into blood and lungs of centuries spent breathing thin air. Alongside this thinning of the air comes a steady, almost mathematical drop in temperature, one that surprises people who assume that because a mountain is closer to the sun, it should somehow be warmer. It is not, and the reason has to do with how the sun actually warms a planet like this one. Sunlight passes through the atmosphere fairly easily, and it is the ground below, warmed by that sunlight, that in turn warms the air sitting closest to it. Air far above the ground has less of that warmed surface nearby to draw heat from, and because it is thinner, it also holds less heat to begin with, the way a sparse handful of embers holds less warmth than a dense bed of coals, even if both are glowing at the same temperature. Climb a mountain, and on average, for roughly every 1,000 feet of elevation gained, the temperature drops by something in the neighborhood of 3 or 4 degrees Fahrenheit. It does not take an especially tall mountain, then, for a climber to pass, over the course of a single day, through a temperature range that would otherwise take a journey of 1,000 miles toward the poles to experience. This is why a mountain near the equator can carry a permanent cap of snow and ice, even while its lowest slopes sit in dense, sweating tropical rainforest, two climates stacked vertically instead of spread across a map. The mountain called Chimborazo in Ecuador captured exactly this idea for the naturalist Alexander von Humboldt, who climbed partway up its slopes in 1802 and sketched what he saw as a series of distinct bands, tropical growth giving way to temperate forest giving way to grassland giving way finally to bare rock and snow, each band with its own characteristic plants and animals, as though the mountain were a single vertical cross-section through many of the Earth's climates at once. Somewhere along that climb, the trees simply stop. This boundary has a name, the tree line, and like so many boundaries in nature, it is not a sharp edge so much as a gradual thinning and struggling, trees becoming shorter, more twisted, more widely spaced, until finally none remain at all. What stops them is not one single thing, but a combination of pressures working together. Growing seasons too short for a tree to complete the slow business of building wood, winds too constant and too cold for delicate new growth to survive, soil too thin and too poorly formed to anchor deep roots. Near that boundary, a traveler will often find a strange and rather moving sight. Trees that are not dead but are bent almost flat against the ground, growing sideways rather than upward, sometimes called Krummholz, a German word that simply means crooked wood. These are ordinary trees, the same species that stand tall and straight lower down the slope. But at this exact elevation, on this exact exposed ridge, they have been shaped over decades by relentless wind and ice into low, sprawling forms, hugging whatever shelter the ground itself provides, because any branch that dares to rise too high above that shelter is simply killed by the cold and the constant scouring wind. Above the tree line lies what is often called the alpine zone, a landscape that at first glance can look almost lifeless. Gray rock and thin gravel and patches of snow that never fully melt even in the warmest part of summer. But look more closely. Get down close to the ground, the way a person might kneel to examine something small, and this apparent emptiness resolves into an entire community of plants, remarkably specialized for exactly this harsh, wind-scoured, oxygen-poor world. Many alpine plants grow low and dense, forming tight cushions or mats pressed close against the rock, a shape that helps them avoid the worst of the wind and also lets them trap a small pocket of slightly warmer, calmer air right at ground level, a kind of personal greenhouse only a few inches deep. Their growing season may last only a matter of weeks. So many alpine flowers do something a lowland gardener might find remarkable. They begin forming their flower buds the previous year, tucked away and protected through the long winter, ready to burst into bloom within days of the snow finally melting, because there simply is not time to start that process from scratch once summer briefly arrives. The animals that live in this thin, cold, wind-scoured world carry their own quiet forms of specialization. The pika, a small relative of rabbits that lives among the loose rock fields of many high mountain ranges, spends its short summer gathering and drying stacks of grass and wildflowers into miniature haystacks tucked beneath the rocks, a kind of larder built to see it through a winter when nothing green will grow at all. Mountain goats, despite their name closer kin to antelope than to the goats of a barnyard, navigate cliffs and ledges so narrow and steep that a human observer can find it almost uncomfortable to watch. Their hooves built with a soft, gripping inner pad surrounded by a hard outer rim, an arrangement not unlike a climbing shoe, part cushion and part edge. Perhaps strangest of all are the bar-headed geese, which each year cross directly over the Himalayas during their migration, flying at altitudes where the air holds barely a third the oxygen found at sea level. a feat that would leave most birds, and certainly most mammals, entirely unable to function, made possible by blood and lung adaptations refined over a very long evolutionary history of pushing higher than seems reasonable. What emerges from all of this? The thinning air, the falling temperature, the retreating trees, the specialized plants and animals clustered above them, is a landscape organized less like a single place and more like a stack of very different places, one sitting directly atop another. And because each isolated peak repeats this same stacking in its own particular way, separated from its neighboring peaks by valleys of warmer, lower ground that its alpine specialists cannot easily cross, a single mountain summit can become something close to an island, a small patch of cold habitat marooned in a sea of warmer terrain, cut off just enough for just long enough that the life clinging to it begins, slowly, to become something slightly its own. And yet these islands of thin air are not fixed in place the way true islands are, resting on some ancient and stable seabed. A mountain is, in a very real sense, an event still happening, and the same slow forces that lifted it skyward over millions of years continue to work on it every single day, in ways too gradual for any pika or mountain goat to notice, punctuated every so often by moments that are anything but gradual. It may help, in thinking about mountain hazards, to hold two very different timescales in mind at once, because much of the confusion people feel about earthquakes and landslides and avalanches comes from mixing them up. The first timescale is almost unbearably slow. Tectonic plates, those vast plates of rock that make up the Earth's outer shell, drift against one another at a pace often compared to the speed at which a fingernail grows, a few centimeters a year, sometimes less. Where two plates push against each other, as happens along much of the length of the Himalayas or the Andes, the rock does not simply slide smoothly past itself. It catches. Friction holds the two sides locked together, even as the deeper, more flexible rock beneath continues its patient, plodding push. Stress accumulates in that locked zone the way tension builds in a rope being slowly, steadily pulled taut, or the way pressure builds in a knuckle bent gradually backward, past comfort, past its resting position, toward a point where something eventually has to give. That giving is the second time scale, the sudden one, when the accumulated stress finally exceeds the strength of the rock holding it. The lock breaks, and the two sides slip past each other all at once, releasing in seconds energy that took decades or centuries to build. This is an earthquake. The ground does not so much shake randomly as it rings, rather like a struck bell, sending waves of motion outward through the solid earth in every direction from the point of rupture. Near a mountain range built by exactly this kind of collision, earthquakes are not really a separate hazard layered on top of the mountains. They are, in a sense, the mountain's heartbeat, the visible pulse of the very process that built the peaks in the first place, each one a small, violent settling of accounts between two great slabs of rock that have been leaning on each other for a very long time. It is worth sitting with how strange this is, if you let yourself really think about it. The same collision that produces something as serene as a snow-capped ridge glowing pink at sunset, something that mountain climbers travel great distances and spend great sums of money simply to look at, is also the collision that occasionally shakes a village to pieces in under a minute. Slowness and violence are not opposites here. They are two expressions of the same underlying process, observed at two different speeds. The way a river looks perfectly still from a distance, and yet, up close, is a chaos of moving water every moment of every day. Earthquakes matter for a second reason too, because the shaking itself is often not the most dangerous part of what follows in steep terrain. A mountainside is, structurally speaking, a pile of loose material sitting at an angle, held in place by friction, by the interlocking of rock and root and soil, by whatever equilibrium gravity and geology have worked out between them over time. Shake that pile hard enough, even for a few seconds, and the equilibrium can break. This is how a landslide begins. Sometimes the trigger is an earthquake. Sometimes it is nothing so dramatic, simply a period of heavy rain soaking into a slope until the soil grows heavy and saturated, the way a sponge holds water until it can hold no more, and the added weight, combined with the way water reduces the friction between soil particles, is enough on its own to send a section of hillside sliding downward. Landslides come in a range of forms, and the difference between them mostly comes down to what is moving and how much water is mixed in with it. A slower landslide might involve a slab of soil and vegetation creeping downhill over the course of hours or days, sometimes slowly enough that people can walk away from their homes rather than be caught inside them. A faster one, sometimes called a debris flow, behaves almost like a thick, moving batter, a slurry of mud, rock, broken trees, and water rushing down a valley at speeds that can outrun a person on foot, carrying enough force to move boulders the size of cars and to strip a hillside down to bare rock as it passes. Rockfalls are a related but distinct hazard, usually smaller in scale, but no less real for the people standing beneath them. Where landslides typically involve loosely packed soil and debris sliding as a mass, a rockfall is closer to what the name suggests: individual blocks or boulders of solid rock breaking free from a cliff face and falling, bouncing, or rolling down a slope. The cause is often something patient and unglamorous: water seeping into a crack in the rock, freezing overnight, expanding as ice always does, and prying the crack open just slightly wider than it was the day before. Repeat that freeze and thaw enough times, across enough winters, and eventually a piece of the cliff that has sat in place for centuries simply lets go, sometimes with no warning at all beyond a faint clatter of smaller stones a moment before. Avalanches operate on a similar logic to landslides, but with snow standing in for soil and rock, and they tend to happen on a much faster clock. A snowpack, over the course of a winter, builds up in layers, and those layers do not always bond well to one another. A layer of soft, loosely packed snow, buried beneath a heavier, denser layer, can behave almost like a shelf, holding weight above it until it suddenly does not. When that weak layer fails, the snow above it can release all at once across a wide slope, sometimes triggered by nothing more than the added weight of a single skier crossing at just the wrong point, or by the vibration of a loud sound, or, again, by an earthquake. What makes avalanches especially disorienting to think about is the speed involved. A slope that looked entirely calm and solid a moment before can be moving at speeds approaching those of a car on a highway within just a few seconds, carrying enough force and enough mass to flatten trees and bury everything in its path under snow that, once it stops, can set almost as firm as concrete. Volcanic mountains add one further layer of hazard on top of all of this, because the danger from a volcano is rarely limited to the eruption itself. One of the more counterintuitive dangers, and one that has caused some of the deadliest disasters in mountain history, is called a lahar, a fast-moving mixture of volcanic ash, rock, and water that flows down a mountain's slopes and valleys, much like the debris flows already described, except that a lahar does not necessarily require an active eruption to happen. Loose volcanic ash sitting on a steep slope can be mobilized by nothing more dramatic than heavy rainfall or the sudden melting of snow and ice on the mountain's upper reaches, sometimes years or even decades after the eruption that deposited the ash in the first place. The ash, fine and loosely packed, mixes with water into something with the rough consistency of wet concrete, and that mixture then follows the shape of the valley downhill, gathering speed and mass as it goes, capable of traveling many miles from the volcano itself and reaching towns that might not have seen so much as a plume of smoke on the horizon that day. And yet, despite all of this, mountains have never simply been obstacles or hazards to the people who lived near them. For as long as there have been humans capable of looking up, mountains have also been landmarks, gods, sources of wealth, and puzzles worth solving, and the story of how people have moved through, worshipped, dug into, and finally measured these enormous landforms is its own kind of history, layered almost as thickly as the rock itself. Before compasses and satellites, a distant peak was often the most reliable thing a traveler had. A mountain does not move, does not disappear behind clouds forever, and can often be seen from many days' journey away, which made ranges like the Alps or the Andes into something like enormous, silent signposts. Traders, crossing the ancient network of routes, now loosely called the Silk Road, learned the shapes of particular peaks the way a sailor learns a coastline, using them to judge how far they had come and how much farther remained before the next pass or the next town. In the Andes, the Inca built a road system stretching many thousands of miles through some of the most vertical terrain on Earth, complete with stone staircases cut directly into cliff faces and suspension bridges woven from grass fiber that were rebuilt every year, allowing runners to carry messages across distances that would otherwise have taken far longer to cross on foot. None of this was easy. High passes are cold, thin in oxygen, and often closed by snow for large parts of the year. But a difficult path over a mountain was still, very often, shorter and safer than a long detour around one. It is worth pausing on why so many cultures, entirely independently of one another, came to treat their tallest peaks as sacred rather than merely tall. Mount Kailash in Tibet is considered holy by several religious traditions, and to this day it has never been climbed, not because the climb is impossible, but because doing so is considered deeply disrespectful. Mount Olympus was, in Greek tradition, the literal home of the gods, its upper slopes wrapped in cloud in a way that must have looked, to someone standing in the valley below, exactly like a curtain drawn across something not meant to be fully seen. Mount Fuji has been regarded in Japan as a sacred site for over 1,000 years, climbed by pilgrims in white robes as an act of devotion rather than sport. There is a simple, almost obvious logic to this pattern once you notice it. A mountain is the closest most people will ever come to touching the sky. It disappears into weather that behaves differently than the weather at ground level, and it holds its snow long after the surrounding land has gone green, all of which made it entirely reasonable, in a world without satellites or weather balloons, to imagine that whatever forces governed the heavens might live, or at least visit, somewhere near the summit. Mountains have also been treated, quite separately from any sense of the sacred, as something to be opened up and taken from. The silver deposits inside Cerro Rico, a mountain in what is now Bolivia, were so vast that the wealth extracted from them helped fund the Spanish Empire for well over 2 centuries, and the mining town that grew up at its base, Potosi, became for a time one of the largest and richest cities anywhere in the world, built entirely on ore hauled out of a single mountain by hand. Coal seams running through the Appalachian Mountains in the eastern United States shaped entire regions of that country's economy and culture for generations, with towns rising and falling depending on which seam was still profitable to dig. Salt, gold, copper, tin, mountains around the world have been tunneled into and hollowed out in pursuit of, nearly every valuable mineral known, and the scars of that mining, terraced hillsides, collapsed shafts, towns that emptied out once the ore ran thin, remain visible in mountain landscapes on every inhabited continent. At the same time, and for almost the opposite reason, people began climbing mountains not to take something out of them, but simply to see what was at the top, and to look outward and upward from a place few others had stood. This impulse, now called mountaineering, has a fairly traceable beginning. In 1786, a doctor named Michel Paccard and a crystal hunter named Jacques Balmas became the first people recorded to reach the summit of Mont Blanc, the tallest peak in the Alps, and their success is often treated as the symbolic start of climbing as its own pursuit rather than a byproduct of hunting or trade. Through the following century, climbers steadily worked their way up peak after peak across the Alps, forming clubs, publishing accounts, and developing equipment and technique as they went, until eventually attention turned toward the highest mountains on Earth, in the Himalaya and the Karakoram, where the air itself becomes a serious obstacle. It would take until 1953 for Tenzing Norgay and Edmund Hillary to become the first climbers confirmed to reach the summit of Mount Everest, a mountain that had by then already claimed a number of lives, including that of George Mallory, who disappeared high on the mountain decades earlier under circumstances still not fully resolved. The very fact that we can say Everest is the tallest mountain on Earth, rather than simply the tallest one anyone happened to notice, depends on a separate and less celebrated kind of achievement, the patient work of mapping and measuring. In the early 19th century, British surveyors undertook what became known as the Great Trigonometrical Survey of India, an effort to measure the exact shape of the land using a method called triangulation, in which surveyors set up enormous chains of interlocking triangles across the landscape, measuring angles from known points to calculate distances and heights with remarkable precision, all without modern instruments, using little more than theodolites, chains, and an enormous amount of careful arithmetic, done entirely by hand. It was a mathematician working on this survey, Radhanath Sikdar, who is generally credited with first calculating, from a distance of well over 100 miles, that a previously unremarkable peak, then labeled only as Peak 15, was in fact taller than every other mountain yet measured on Earth. The peak was later named Everest, after a former head of the survey, a naming choice that Everest himself is said to have mildly objected to, feeling a mountain in Tibet and Nepal ought to keep a name already used by the people who lived near it. Measuring a mountain's height sounds, at first, like a simple matter of holding up a very long tape measure, but it depends on agreeing what counts as the bottom. Height is conventionally measured from sea level, but sea level itself is not a fixed, flat plane wrapped evenly around the planet. It bulges and dips slightly, depending on gravity, temperature, and the shape of the seafloor beneath it, which means that even the reference point used to measure a mountain's height has had to be defined and refined over time using increasingly precise tools, from barometric pressure readings in the 19th century to satellite positioning today, occasionally revising a mountain's official height by a few feet in either direction as measurement techniques improve. None of this exploration, worship, mining, or measuring would have amounted to much if people had been unable to move through the mountains in any practical, repeated way, and it is to that challenge of actually building roads and tunnels through rock that never wanted to be crossed that we can turn next. Even before engineers worked out how to blast a road through solid granite, another set of researchers was chasing a different question, one that had nothing to do with crossing a mountain and everything to do with figuring out how it got there in the first place and how long it took. It is one thing to stand at the base of a peak and admire its bulk. It is another thing entirely to ask when that bulk arrived, whether it is still arriving, and how a person sitting in a laboratory hundreds of miles away could possibly know the answer to either. The earliest clue came not from instruments, but from shells. When Charles Darwin traveled through the Andes during the voyage of the Beagle in the 1830s, he found fossilized seashells embedded in rock more than 12,000 feet above sea level, a discovery that stopped him in his tracks because those shells had unmistakably formed on an ocean floor, and an ocean floor had no business sitting near the top of a mountain range. The explanation, once it settled into place over the following century, was that the rock itself had once lain beneath the sea, and had been lifted, slowly and without ceremony, thousands of feet into the sky. Marine fossils found on mountains all over the world tell some version of this story, and because many of those fossils belong to species that lived only during specific, well-documented stretches of geologic time, geologists can use them almost like a date stamped on the bottom of an old photograph, narrowing down not just that uplift happened, but roughly when the rock being uplifted was still underwater to begin with. Fossils can only tell part of the story, though, because they only appear in rock that was hospitable to living things, and much of what makes up a mountain range never held a single shell or bone. For that, geologists turn to the minerals themselves, and to a technique that sounds almost too convenient to be real, which is that certain elements trapped inside certain crystals decay into other elements at a rate so steady, so entirely unaffected by heat, pressure, or the passage of empires, that the ratio between the original element and its decayed product functions as a remarkably reliable clock. Potassium, locked inside a mica crystal, slowly becomes argon. Uranium, locked inside a zircon crystal, slowly becomes lead. Nobody has to wind these clocks or check that they are keeping accurate time, because the rate of decay is a fixed property of the atom itself, as unchanging as gravity. What makes this useful for studying mountains specifically is a wrinkle called the closing temperature, the idea that many of these clocks do not start counting the moment a mineral forms deep underground, but only once the surrounding rock cools below a certain threshold, and rock only cools that much once it has been carried close enough to the surface to feel the chill of open air rather than the ambient heat of the deep crust. So when a geologist collects mineral grains from a mountainside and runs them through what is called thermochronology, they are not simply asking when the rock formed, they are asking when it finished its long elevator ride upward, when it crossed the particular depth at which its internal clock was allowed to start ticking. Comparing several minerals from the same rock, each with a different closing temperature, produces something close to a time-stamped record of the rock's entire ascent, a set of snapshots preserved in grains smaller than a grain of sand. Sediment tells a complementary story, one written not in the mountain itself, but in the debris shed from it. Every mountain range is also, quietly and continuously, a mountain range being worn away, and the material removed by rain, frost, and rivers does not simply vanish, it travels downstream and piles up somewhere else, in a delta, a lake bed, or a sedimentary basin, layer after layer, settling like sediment in the bottom of a glass left undisturbed. By drilling into these accumulated layers and measuring how thick they are, how quickly they built up, and how coarse or fine the particles within them are, researchers can estimate how fast the mountains that supplied that material were being ground down at any given point, and a sudden shift toward thicker, coarser layers often signals a period when uplift accelerated and erosion had more freshly exposed rock to chew on. A mountain's history gets written twice this way, once in the peaks that remain and once in the debris that left, and the two records, read together, tend to agree with each other in a way that gives geologists confidence They are looking at something real rather than a coincidence. All of this concerns the deep past, millions of years compressed into a handful of mineral grains. But modern instruments have made it possible to watch mountains move in something much closer to real time. Networks of continuous GPS stations, bolted into bedrock across ranges like the Himalayas or the Andes, track their own position to within a few millimeters, day after day, year after year, and over time those tiny wobbles add up into a clear trend, the ground beneath the receiver creeping upward, or sideways, or both, at rates that can be measured in centimeters per year, roughly, coincidentally, about the speed at which a fingernail grows. Satellite radar offers a complementary view from above, using a technique called interferometry to compare radar images of the same patch of ground taken months or years apart, detecting shifts in elevation so small, sometimes just a few millimeters, that they would be invisible to almost any other method, and revealing not just steady creeping uplift, but the sudden lurches that come with individual earthquakes, moments when decades of slowly accumulated strain release all at once. Seismology adds another layer, because earthquakes themselves are direct evidence of mountain building in progress, each one a small, violent record of rock breaking and shifting along a fault, and by studying the pattern, depth, and frequency of these earthquakes over years, researchers can map where stress is still building beneath a range and estimate how much of it is being relieved gradually versus stored up for some future, larger event. None of these methods, fossils, minerals, sediment, GPS, radar, or seismology, gives a complete picture on its own, which is why modern studies of mountain growth tend to rely on models that combine all of them, computer simulations that take the scattered, partial evidence from a dozen different techniques and knit it into a single, coherent estimate of how fast a range is rising, how fast it is eroding, and whether those two forces are currently balanced or whether one is winning. That last question, whether uplift or erosion is winning, brings us back around to something touched on earlier, the surprisingly slippery matter of a mountain's height. Because even with satellites capable of measuring millimeter-scale shifts, deciding on a single, official number for how tall a mountain is remains oddly complicated. Consider Denali in Alaska, whose official height was revised downward in 2015, not because the mountain shrank, but because a new GPS survey replaced an older method based on barometric air pressure that turned out to have been slightly less accurate all along. Or consider the question of what actually counts as the summit, since some peaks are capped year-round with snow and ice many feet thick, meaning the highest point a climber stands on is not necessarily the highest point of solid rock underneath, a distinction that mattered enough that Nepal and China spent years negotiating before agreeing, in 2020, on a new official height for Everest that accounted for both the rock and the snow. Even the ground itself is not perfectly reliable, since a large earthquake can lower a summit by an inch or raise a neighboring ridge by several feet within a matter of seconds, which means a mountain's height is never really a single fixed fact waiting to be discovered, so much as a careful, temporary agreement between rock, ice, gravity, and whoever happens to be doing the measuring that week. And whatever number ends up printed in a guidebook, none of it does anything to soften the granite underfoot for the people who still have to find some way across it. So let the measuring rest for a moment, the surveyors and their satellites, the arguments over rock versus snow, and let's instead just watch the whole slow system turn, the way you might watch a wheel that has been spinning so long it looks almost still. Somewhere beneath a mountain range right now, two plates of ancient rock are pressing against each other at a pace slower than your fingernails grow, an inch or two a year, patient beyond anything a human life can really hold in mind, and where they meet, rock that was once seafloor mud or a coral reef or the ash of some forgotten volcano gets folded and lifted and shoved upward into the cold air, a few millimeters some years, nothing at all in others. Occasionally a sudden shudder of feet in a single earthquake that makes 1,000 years of patient inching look almost hasty by comparison. That is the mountain being built, slowly, unevenly, by forces with no particular hurry, and almost the moment that rock reaches the air, before it has even finished rising, something else begins working against it. Rain falls, and where it falls it finds every crack, every weakness in the stone, and it seeps in, and if the nights are cold enough it freezes there, and ice takes up more room than water, so the crack widens, just slightly, and over centuries that slight widening becomes a fracture, and the fracture becomes a fallen slab, and the fallen slab becomes gravel, and the gravel becomes sand, and the sand rides a stream down into a river, and the river carries it, grain by grain, toward some lowland or some sea, where it will settle, and layer upon layer, over millions of years, harden back into rock again, waiting, perhaps, for some far future collision to lift it back into mountains once more. The rock does not know it is part of a cycle. It simply responds, at every moment, to whatever is pressing on it, upward or downward. And the shape we call a mountain is just what that responding looks like when we happen to be watching. Ice does its own slow work in the meantime, not only prying rock apart, but gathering into rivers of its own, glaciers that creep downhill under their own patient weight, carrying boulders the size of houses in their grip the way a conveyor belt carries packages, and scraping the valleys beneath them into the wide U-shapes that a sharp V-shaped stream valley could never make on its own. When a glacier finally melts back, sometimes after an ice age tens of thousands of years long, it leaves behind a landscape rearranged, ridges of dumped rubble called moraines, boulders stranded far from any other rock like theirs, a whole quiet signature written in stone and gravel that a geologist can read the way the rest of us might read handwriting, learning not just that ice was here, but roughly how thick it was, and which direction it was moving, and how long ago it let go. The weather up there, meanwhile, is its own kind of sculptor and its own kind of storyteller. Wind that has nothing to slow it down scours the exposed ridgelines bare, while air forced to rise over a summit cools and drops its moisture as snow or rain on the windward side, leaving the far side dry, sometimes dry enough to be called a desert, all because a single ridge of rock stood in the path of air that would otherwise have carried its moisture much farther. That rain shadow shapes what grows and what does not, and what grows shapes what animals can live there, and what animals live there shapes, in small ways, how the soil itself is built, which roots hold it, which burrows aerate it, which grazing keeps grasses cropped low instead of letting forest take over. Rock, ice, weather, water, life, each one leaning on the others, none of them separable if you actually try to explain any single mountainside honestly. And woven through all of it, threaded so completely into the landscape that it can be easy to forget it is there at all, is water finding its way downhill, the same water, more or less, that has been cycling through the planet's mountains for as long as there have been mountains and an atmosphere to rain on them. It falls as snow on a high ridge, sits through a winter, melts in a slow spring thaw that feeds a stream too small to have a name on any map, joins other such streams until it becomes a river wide enough for boats, carries with it, the whole way, some fraction of the mountain's own substance, ground down to sediment too fine to see, delivering it eventually to a floodplain, or a delta, or the sea, where new rock will someday, in some unimaginably distant era, begin to form from what a mountain, right now, is quietly giving away. It is worth sitting with, for just a moment, how many different timescales are folded together in that single picture. The plates move at the speed of growing fingernails. A glacier moves at the speed of a very slow walk, if it moves at all in a given hour. Water in a mountain stream moves fast enough to be genuinely dangerous to wade across. Wind moves faster still. And somewhere in the middle of all of that, moving at the speed a human body actually moves, walking, breathing, resting, a person can stand on a ridge, and without straining to imagine it, sense that everything underfoot is both perfectly solid and, on some other clock entirely, perfectly fluid, rising and falling and rising again, over and over, longer than any single mountain range has ever lasted. Because no range lasts forever, not even the ones that feel, from where we stand, like the most permanent things on earth. Every range that has ever risen has also, eventually, worn down, sometimes over tens of millions of years, sometimes faster if the climate turned unusually wet or unusually cold at just the wrong moment for its particular rock. The old, rounded mountains of somewhere like the Appalachians were once, by most estimates, as tall as anything standing today, jagged and young and impossibly high, before hundreds of millions of years of patient rain and frost and river work smoothed them down into the gentler, forested hills a person can walk comfortably today, without ropes or oxygen. The tall, sharp ranges we now think of as the dramatic ones, the Himalaya, the Andes, the Alps, are simply younger, still early enough in that same long process that their edges have not yet been sanded soft. Give any of them enough time, more time than is easy to hold on to in any real way, and they too will settle into something gentler, while somewhere else on the planet, some patch of ordinary-looking ground will already be starting, without any fanfare at all, to rise. And all of that, the folding and the freezing and the wearing away, all of it, has been happening this entire time you have been lying still, listening, breathing in and breathing out, each breath taking in a little of the same air that has drifted, over years, across ridgelines and down valleys, and through the thin cold layers above a summit somewhere. You do not have to do anything with any of this. You do not have to remember which range is folded and which is faulted, or how tall Denali is measured to be this decade, or what exactly a moraine looks like. You can simply let the breathing continue on its own, slow and unhurried, the way a river keeps moving toward the sea, whether or not anyone is watching it, the way a mountain keeps rising and wearing away in the same patient motion, too slow to see, too steady to stop. Let your shoulders soften into whatever is holding you. Let your breath find its own quiet rhythm, in and out and in again. No need to guide it, no need to think about it at all. The mountains will still be there in the morning, rising by some fraction too small to measure, wearing down by some fraction too small to notice, exactly as they were before you started listening, exactly as they will be after you fall asleep. Rest well.